You're doing it.
Wait, I need to.
Okay. Thank you all for coming. So today it is my pleasure to introduce Rongjie Lai, who's at RPI. Rongjie, his work is in a lot of areas, including scientific computing, optimization, PDEs, geometry, learning on geometric structures. And he's also the winner of a number of grants and awards, including an NSF Career Award. So today, Rongjie is going to be talking about computational mean field games. Take it away.
All right. Thanks so much, Alex. And thanks so much for the invitation from the organizers. And it's my great pleasure and honor to be able to share some of our recent research in my group and also with my collaborators. This is a joint work with my student. I don't have, okay. My student, Jia Yu and Bill Huang, these two outstanding students, they made a majority contribution. If anything good, it's because of them. Anything bad is just blame me. And also my collaborator, Jay Chen from IBM and Wu Chen at the University of Southern Carolina and Stan Osher from UCLA. So this is supported by, so my group is supported by two NSF grant, and Stan Osher's group is majorly supported by their Muri grant. Oh, by the way, the first student, Jia Yu, she's on the market looking for postdocs. If any of you got convinced, if you have an opportunity, please let me know. Anyway, so here's some introduction. So the problem we care about is essentially some kind of optimal control problem in terms of the population behaviors. And I show some pictures. The first picture, as you can say, is so-called a multi-group path planning. So imagine you have two groups of let's say birds or drones that fly in the space. So they would like to avoid some possible obstacle. At the same time, they don't want to have any kind of a collision between groups. So think about a autonomous vehicle, autonomous drone flying in space. You hope to design some kind of a methodology to guide the trajectory of this group flying in space. And in the middle, also something related, and the bottom picture I showed is called a crowd motion. So you have also a group behavior. You have a group of, let's say, people. They would like to move outside of the classroom, for instance. So definitely, as you can see in the picture, the classroom have some kind of obstacle. So you want to design some kind of optimal strategy, such as this flow can move quickly outside of the classroom to minimize some kind of a cost. And also now it's pandemic, right? If you think about the resource allocation and the source is going to redistribute on the global, so you have this and that sort of constraint or limitation. You want to avoid some kind of obstacle, at the same time minimize certain cost. All of this is related to understand or develop a competition strategy or about this group-wise population behavior using some kind of optimal control ideas. The other one is also very interesting, is sort of related to this transport, density transport, and also a deep generative model, which is extremely popular recent years in the data science. So if you think about all those pictures, if you view those group behavior as some kind of a density moving around in the space, and all of this satisfies some kind of a general formula in the following sense. Basically, you say we're gonna design some kind of a optimized choice of the popular behavior, such as this choice can minimize some kind of cost. The cost usually can be written as different components. Here I write down, for instance, the first component is so-called the kinetic energy. Then you have some interaction among the groups, and you may have certain kind of a destination or target density you would like to go. And of course, all this moving population density moving behavior in the space should satisfy some kind of a population dynamics. So that's sort of the problem we are interested in. So if you write down this in a more mathematical way, and you can have this sort of more general framework. It's pioneered by a group of mathematicians, and this is called the mean field gain model. So essentially, the mean field gain model is looking for the solution of such a optimization problem. So you have this, each single player should optimize the following cost. The cost, as I show you, has three components. L, you can view this as some kind of kinetic energy, and F is sort of the interaction, and G is the termination, or how do you move your given density, move towards the sort of expected target that you would like to go. And you want to solve the problem in a way that all this different single player, different agent, they move in the space and eventually achieve the so-called Rongjie equilibrium. Essentially, the Rongjie equilibrium satisfy first each of the single player should give you the minimal cost of the desired objective function. At the same time, the whole population dynamics should follow the sort of the optimal control. So people actually show that if you write down your population dynamics satisfy the so-called Rongjie equilibrium, you will have this density and the control or the so-called value function will satisfy the following two system equation. One is called the Hamilton-Jacobi-Bauman equation, and the other one is called the Fokker-Planck equation. Here, for simplicity, I sort of shut down the noise. You only see this continuity equation, the second equation. I don't have my cursor somehow. Oh, here. So here, if you have some noise, and here you will see the contribution of the Laplacian operator here. So this is related to, if you think about this Hamilton-Jacobi-Bauman equation actually propagate the information back to the initial, and this Fokker-Planck equation push the information starting from the initial density to the target density you would like to have. This is quite similar as the sort of mimic the behavior of the deep neural networks. But you have the training starting from the initial, and the deep network it's going to forward the propagating information all the way to the very last layer. Then you have the training data. You ask BP to back propagate the information back to the initial to sort of optimize the parameters. And this two systems, forward and backward, they are working together is very, very interesting, at least to me. So this is sort of the problem we are interested in. Now, to be more precise, so we are interested in this sort of so-called variational mean field gain. So in a sense that if your interaction term F satisfies this kind of variational formula, so F is a derivative of some kind of a potential, and G is also derivative of some kind of a categorical G, then you can say the previous problem I write down is actually reduced to this kind of variational PDE problem in a space. So even more specifically, you choose this interaction cost F is 0, and G is like very, very strong, which means you ask the initial density is some given density, and the target density is also equal to the other given density. This is going to relate to this very famous and very popular problem is called the optimal transport. Essentially, people sort of minimize the kinetic energy of the flow in the space, and such that the flow is going to satisfy this population dynamics, the so-called continuity equations. So this kinetic energy, as we know, this basically will give us geodensity of the flow in the probability space. So this is essentially the problem we're trying to solve. Of course, this variational mean field gain problem is a generalized version of the optimal transport. In other words, if we build up a solver for the mean field gain problem, and that solver can be naturally applied to solve the mean field gain problem. So that's the problem we like to solve. So if you have any question, please feel free to stop me at any time. Now, our objective. So our objective is we would like to develop a sort of computational scalable algorithm using the conventional method, especially when we talk about lower dimension, let's say 2-dimension or 3-dimension case, and also maybe combine with some recent advance of the deep learning method to solve this high-dimension variational PDE problem. So we know for the high-dimension variational PDE problem, conventional method is really hard because of the curse of dimensionality, you discretize the space, then that memory consumption is really, really high, then it's really hard. And we hope some idea borrowed from deep learning may give us some hope. And we hope our efficient algorithm can be good and also with some kind of reasonable theoretical guarantee. And of course, we would like to, if we solve this sort of high dimension variational mean field game problem using deep learning method, then we hope we can bridge the connection to the deep generative model, and hope it's not only deep learning can help solve the mean field game problem, maybe the wisdom from the mean field game model can help improve the deep learning model. So that's the other sort of thing in our mind, and eventually we hope we can apply our solvers, our techniques to a real life problem. So this talk will share you our preliminary effort. So we may or may not be able to achieve all of them, but hopefully this is a sort of a convinced way. So now the talk outline today, I'm gonna starting from a conventional method to solving a lower dimension mean field game problem in the Euclidean space. Then I will quickly move to deep learning based method in the high dimension setup. Then if I still have time, I'm going to talk about some numerical method to solve mean field game problem on the sort of lower dimension remaining manifold. If I have more time, I'm going to talk about something else, but I'm not sure. Okay, let's see. So let me say a few words about the literature in the conventional numerical methods to solving the optimal transport and mean field game problem. So I'm going to majorly focus on the Bernier-Benamou, the dynamic formula of the optimal transport, and also its generalization for the mean field game problem. So there's a rich history about the, for instance, optimal transport. There's a linear programming version. I won't mention those things about at all. So two special algorithm in the literature. One is called the augmented Lagrangian based methods. The other one is called the prima duo based method. So essentially, both of those methods, they are trying to remember our previous variational PDE problem. There's a constraint about the continuity equation. So what they do is they use some optimization strategy to sort of solve that constraint optimization problem. And the augmented Lagrangian basically introduced augmented Lagrangian to handle this PDE constraint. And the prima duo is also introduced this using this combine this prima duo based method to handle this PDE constraint problem. So if you take a look at this problem, so right now the setup is actually the optimal transport. So if you take a look at this problem, then each of this augmented Lagrangian or prima duo, you have to solve the sub-optimization problem. And here you can easily see if you, in terms of the sub-optimization of the row problem, you do the divergence theorem, you will actually see you have to solve the element-wise, entry-wise, you have to solve the cubic equation. And similarly, the situation happened when you apply this prima duo based method, and element-wise, you have to solve some cubic equations. So those algorithms are actually very nice, give you some very nice result, and it's very efficient. But because of the subproblem is related to the cubic equation, so it's not easy to do perturbation analysis. In other words, if you want to show, I give a discretization, if my mesh is dense and dense when the mesh converge to the continuous case, whether my solution actually converge to the continuous solution, it's not easy because the perturbation analysis of the cubic equation is not easy, at least to me. And the other thing is that they force this constraint, this so-called implicit method. They force the constraint implicitly, not explicitly. And plus, if you want to generalize this kind of algorithm to the mean field game setup, which means this cost function here is more general, may or may not have something as nice as optimum transport. You may have a kinetic energy, you may have an interaction energy, you may have some other energy as well. So you have to, each optimization problem, you have to solve some sub-optimization problem. You don't have a closed, you may or may not have a closed form solution as those in the optimal transport, which you have to solve the cubic equations. So those are limitations. And so we would like to say, can we design some other algorithm? Hopefully each sub-optimization problem can have a fast solver. And we hope the algorithm have some is an explicit method, which means each iteration can preserve the mass. We hope that the perturbation analysis can be easily done, and then we can conduct analysis about the convergence. Our convergence means when the mesh is dense enough, then the continuous solution is going to converge the discretized solution is going to converge to the continuous solution. That's what we mean about the convergence. And also we hope our algorithm can be very efficient when we solve a sort of inverse mean field gain problem, which I won't have time to talk about this. So that's sort of the talk that we want to do. So let me quickly say something about this lower dimension Euclidean setup, and now I'll talk about something in high dimension. So our algorithm is actually pretty intuitive. It's very simple. The observation is actually based on this slide. So the idea is the following. So remember that constraint I talked about, the continuity equation is actually a sort of the PDE constraint, but that PDE is actually linear. So one interesting observation is when you update your variables O and M, if you project your variable to that linear PDE, then the solution can be efficiently obtained. So you can actually work on this sort of projection step, write down its set of point, the KKT condition of this guy, and with some simple derivation, we can easily figure out the solution of this guy actually is related to you first solve a Poisson equation, which means you have a faster solver in the Euclidean space. Solve a Poisson equation and take a derivative, and you can go back to that. So this is nice in the sense that this projection step is independent on the choice of the objective function because the constraint is fixed. So this gives us a flexibility. If you whether you solve the optimal transport or you solve the mean field gain problem, you can always apply this faster projection step and do the gradient descent. So that's a very natural, very straightforward algorithm. And it turns out people have not really applied this algorithm in the literature. And we try it, as I mentioned. So we just naively try this projection step. You first compute the gradient, which gives us a flexibility. Even the objective function is not as simple as optimal transport. You may have some interaction term or more complicated term. As long as you can compute the derivatives, you do the gradient descent, then project. And this projection step can be easily solved by, for instance, here is, it depends on the boundary conditions. If we impose this Neumann boundary condition, we can use the faster cosine transformation. It's related to FFT, essentially. You can very efficiently solve them. So then we apply some standard numerical PDE techniques. You use this staggered grade to discretize everything. Now actually we have this discretized algorithm, essentially just a gradient descent, then apply a Poisson solver. You can choose your favorite Poisson solver. Here we essentially use FFT. And we adjust the step size. And this will give us some actually very nice, very simple algorithm. And this is not new, actually. In terms of algorithm itself, it turns out this algorithm is related to this famous algorithm. It's called FISTA, faster iterative software thresholding algorithm. And in the discretized level, given discretization, people know this algorithm is going to converge in terms of this order. So we actually essentially apply this algorithm to the mean field gain, variational mean field gain problem or optimal transportation problem. So as I mentioned, the algorithm is actually very simple and very efficient in the sense that, and also flexible in the sense that the gradient step can be easily computed as long as your objective function is differentiable, and that the projection step is always invariant, no matter what kind of mean field gain you are choosing. And plus, if you are looking for some noise, and that projection step can be easily adapted to some Gaussian noise case, which means you have to solve some kind of fourth order equation, but also can be faster solved by FFT. It's so essentially by harmonic equations. So in addition, because of that, the whole nice Poisson equation solver, we can also combine with the multi-grade or multi-scale strategy to speed up the whole thing. So let me sort of show you some results. Oh, the other thing, the nice thing, as I mentioned, so one of the missing part in the literature, in the existing algorithm, is analyze of the convergence means the discretized solution converge to the continuous solution. So because the way we design, we actually avoid that solution of the cubic equations, which means we can conduct the perturbation analysis. So our algorithm actually, for the first time, we establish in terms of the optimization algorithm, we establish this convergence means your discretized solution, as long as the mass size goes to 0, it's going to converge to the true solution, to the continuous solution we're looking for. So I'm going to skip the details about the proof and the formal statement. If you are interested in, here's the link of the paper. So let me show you some numerical results. This is a numerical result that's in the 2D. So we actually compare, this is an optimal transport case. We compare our algorithm with some existing algorithm in terms of the dynamic formula, as I mentioned. One is augmented Lagrangian based. The other one is essentially prima dual based. It's called a G proxy. In their L2 norm, they use some weighted L2. Therefore, they have this G proxy. As you can see here, so here's the time essentially. And also this multi-level and multi-grade FISTA is also our algorithm. Basically, we use some multi-level multi-grade method to speed up. As you can see, in terms of time, this is our multi-level method is actually is the most efficient. And if you take a look at the mass preservation, and also our method actually gave the best job to preserve the mass, and the feasibility residue also we are better than the existing algorithm. And if you take a look at especially this guy, you can see the multi-level problem compared with the right now the state of art method, the augmented Lagrangian and the G proximity algorithm. Actually, we are about around 20 times faster. So we actually like this result a lot, and this is give us a very, very efficient algorithm. In fact, so here's some video to share you if instead of solving the optimal transport problem, if you do have the obstacle in the space, and this show you if apply the algorithm, we can say the flow can successfully avoid the obstacle and give us the flow as what we expected. And here's another video interpolation between different densities. So as you can say, if you shut down the interaction term and obstacle term, then this is essentially the optimal transport. The first picture is essentially optimal transport. In the middle and the rightmost, I show a different choice of the interaction term. You will see the different choice of interaction will give you different transition paths of the evolution of the density. So we think this might be helpful, especially later on if you do the deep generative model, the density evolution of space, and you've got a different trajectory, then the intermediate flow you have will be different, and then you will have the flexibility to control the basically the direction or intermediate status of the flow. So that's sort of the advantage compared with the optimal transport. Essentially, the optimal transport, you don't have any control about the flow direction. You have the control in the sense that the flow has to minimize the kinetic energy, which give you geodesic. But for this one, you can inject more information, give you the way the flow you would like the flow to go. So far that's the sort of the 2-dimension or lower dimension setup. Where of course we can also solve this on the 3-dimension. So we're thinking about in practice, and it's actually very interesting to solve this problem in the high dimension setup. So here I show you some videos. Let me see if I can call the video. Can I call the video? Yeah, the video here. So the video here is like a 8 group of point clouds. You can think about 8 group of drones flying in space. And they would like to, each opposite direction, they would like to switch the location. So the fly face to each other, and they would like to switch the location, swap the location. So if you don't give it any control, of course, this 2 group will definitely have a collision, right? So in reality, you want this drone flying in space, and in a way that they can actually avoid the collision, which means you want to give some kind of interaction control to design them, they can successfully avoid the collision. If you think about the counter dimension of this problem, each of the group, the fly in the space is 2-dimensional. You have 8 of them. So essentially, this is a 16-dimension problem. So the conventional method is pretty hard to solve because it's a 16-dimension problem. If you discretize the 16-dimensional space, use the Euclidean grid, then the memory consumption is way too high to be able to handle in any modern computers. So that's sort of the challenge. The other one is this robot arm control problem. So the robot arm, they have a different freedom in the joint. So essentially, you want to control the robot arm, move from one location to other location. At the same time, you will want to avoid some sort of obstacle in the space. So if you think about this problem in the feature space, it's actually also a high dimension optimal control problem. So all of this practical problem actually motivate us to think about the high dimension mean field game problem, which will give us very interesting applications. So, but the challenge, as I mentioned, in the conventional method actually is really hard, or maybe it's just impossible, at least to me, to solve this PDE control problem in the high dimension space. So there's a nice paper, Pioneer, one of the first papers solving this high dimension mean field game problem that is pioneered by Lars and Stan Osher and their group. They actually use the deep neural network to approximate the solution of the high dimension variational mean field game problem. So what they're doing is the following. So they use deep neural network to approximate or represent the density function rho, and also the value function h. So they basically have two neural networks, approximate density and approximate the value function. Once you have the value function, you can take the derivatives, you got the control directions. And the other thing is when they impose these two representation of the density and also the value function using neural networks, they need to sort of enforce the continuity equation, as I mentioned, two equations. One is the continuity equation, this partial rho, and this divergence thing is equal to 0, which means the mass preservation. And also there's a Hamilton-Jacobi-Bellman equation on nonlinear PDE they also have to impose. So what they do is they essentially use a penalty-based method to penalize the concern of the Hamilton-Jacobi-Bellman equation and the continuity equation. Then they plug in, use the stochastic gradient descent to solve this optimization problem. And once the problem is done, they have a very nice, beautiful result about solving this in a high dimension problem. This is sort of one of the pioneer work to solve the high dimension problems. So we are thinking about a slightly different way. We're trying to connect this mean field game problem to another deep generative model, and hope this connection can give us sort of two sides. So I should not skip this. We want to say, hope this connection can give us, one is use some deep generative model to solve high dimension mean field game problem. The other one is use the guidance for the mean field game problem. Hey, hope this can give us some way to improve or enhance the performance of the deep generative model. So that's sort of our objective to this high dimension mean field game problem. So let me see briefly about this deep generative model. There is essentially 4 different categories of deep generative models. There's a GAN, generative adversarial network, and a variational autoencoder, and a flow-based method is like normalizing flow, and diffusion model, which is very, very popular recently. And as you can see from the news, you will see papers and scholars that fake like images and pictures and paragraphs and the languages. This is related to this deep generative model. So here, what we would like to do is we want to choose one of such a deep generative model. It's called a flow-based method, normalizing flow. So we want to build up a relation between the normalizing flow and the mean field game problem. As I mentioned, first, we want to employ the expressive normalizing flow architecture to solve the high dimension mean field game problem. Hopefully this can sort of overcome the curse of dimensionality and to tackle the high dimension variational PDE problem. On the other hand, we hope the wisdom or theoretical understanding of the mean field gain problem can give us some kind of guidance to regularize the conventional normalized flow, and hope this can enhance the performance of the normalized flow. So that's our sort of perspective for this setup. So let me say a few words, maybe 1 minute about the normalized flow, just in case, make sure we are in the same page. So the setup of the conventional normalized flow is the following. So suppose you have a data set, Xn, sampled in some distribution, let's say P1 in a space. So we would like to define a flow. We would like to define a flow starting from some base distribution. I say the base distribution could be very simple. For instance, Gaussian. So starting from the Gaussian, we would like to compute a composition of bunch of mappings. This Fi, they're actually nonlinear mappings, to gradually push the density, the very simple density, gradually push the density back to the target density we would like to approximate. Of course, for the target density, we only have the sampling of the target density. So then you have, once you have this sort of architecture of the normalized flow, of course, it depends on what kind of choice of the normalized flow you have. But overall, it's some kind of mapping in the space. And once you have this mapping, you push the mapping to the target, then you ask minimize sort of the divergence. For instance, here I choose KL divergence. That's the standard approach. To minimize the KL divergence between the push forward density and the target density, then you train this network basically. Then the way of parameterize the mapping I mentioned, people have so many different ways. And here I quickly put these names, but you don't have to read them at all. There are so many different architecture about normalized flow. And the one is usually very popular to use is called the coupling flow. Basically, people design some special structure of the coupling flow such as you compute the inverse is very easy, because when you do the estimation, when you push forward the density, there's one step you have to compute the Jacobi of the inverse. So which means when you design the density, the flows, so it works to think about some very nice formula about the flows, such as the inverse of the flow can be easily computed. Then you can estimate the density, and this gives you a nice way to implement the push forward map of the density. Then you can then minimize the KL divergence. So that's the basic idea of the normalized flow. So what we're trying to do is, hey, maybe we can combine some idea here to solve the high dimension mean field gain problem. So if you think about the high dimension mean field gain problem or optimal transport in the dynamic formula of the optimal transport, essentially starting from you have two densities. You have a row 0 and a row 1. So you want to design some kind of evolution of the flow starting from a row 0, gradually change to the row 1. Okay, so that's sort of the idea of the flow as well. So if we can sort of convert the variational mean field gain problem, their evolution of the density in terms of the flow map. Then if we have some idea to approximate that flow map, then we use, if we discretize the time, and each small interval of the time, we use some kind of a normalized flow to approximate the density flow map. Then we put them together, and this naturally will connect to the normalized flow. So that's actually our motivation to say, hey, maybe there's a chance using this normalized flow can solve the high dimension mean field gain problem. So as I mentioned, so here's essentially the idea. So what we do is we rewrite the variational mean field gain problem in terms of the trajectory. So what we do is, so remember each of the agent is going to satisfy the ODE flow in the space. So if you consider about the trajectory of the agent in the space, so the trajectory is going to satisfy this ODE. So we plug in the trajectory back to the variational mean field gain problem. You will see that kinetic energy will be like that, just directly plugging, because the partial F is equal to V, right? Directly plugging. And here then you have this interaction term, also directly plugging, and the matching term usually, for instance, could be KL divergence. We can also plug in. So if you plug in this, you will have some nice trajectory-based formula. And one big advantage if you write it in this way is that this variational PDE constraint, the PDE constraint that rho t plus divergence m is equal to 0, that PDE constraint actually can be solved in this trajectory-based formula. And this will give us some nice advantages. Think about the pioneer work I mentioned. They actually use a deep neural network to parameterize the density and also the value function. So they have to penalize the sort of Hamilton-Jacobi-Bellman equation and the continuity equation in the training. But if you write down this trajectory-based formula, this equation automatically can be satisfied, which means we don't need to do that. And this gave us some advantage. And later on, if I show the numerical result, you will also see this actually can enhance some accuracy. So then we can discretize, as I mentioned. So you discretize in terms of time, then you got to discretize the formula. So you plug in, you have this the derivative, you discretize standard, the discretize the time, and you can actually show very standard way to show the approximation of behavior. And meanwhile, you can also plug in terms of time discretization to the interaction term and also the matching term. So now this nothing to do with the deep neural network yet, right? I'm just saying I can use a different point of view of the variational mean-field gain problem. I just rewrite the variational PDE problem to be the trajectory-based approach. But if you have any other standard solver can parameterize the trajectory, you can just plug in and do it. What we're choosing is using the normalizing flow to parameterize this trajectory. So here's a connection to the normalizing flow. So we say for each given agent, the agent is actually satisfy this ODE in the space. Of course, this ODE is you have to determine the control, right? To determine the control is also part of the problem. So if we define the flow map, so if you discretize the time, flow map between Ti and Tj, if I call it phi Ti to Tj, as I write down here. So the trajectory actually can be written as the decomposition or composition of this flow map because the ODE satisfies the semi-group property. So if you take a look at this decomposition, this is exactly similar, exactly the same as that previous normalizing flow model. Basically, normalizing flow is also write down the mapping, the whole mapping as a composition of a bunch of mappings. And here, each of the mapping is actually our flow map. So this is give us a connection to use the normalizing flow to actually approximate or parameterize this flow map and plug in this trajectory-based formula. So that's the whole idea, in fact, that what we do is just to plug in the normalized flow to the trajectory-based formula and run the optimization problem and see how it goes. So that's essentially idea. So the other thing I want to mention is, the other direction, as I mentioned, if you think about this normalized flow you're plugging, and in terms of the trajectory formula of the variational mean-field gain problem, there is for instance, one term is called the kinetic energy. If we discretize the kinetic energy, you can actually see that, in fact, this is the kinetic energy we're gonna minimize, okay? So you can actually do some derivation. You will say, hey, if you actually control or compress the kinetic energy, if you do this derivation, you will say the flow map, this Fk is actually the flow map. The flow map, the difference between X and Y, the input X and Y actually can also be controlled. What does that mean? That means essentially if you do this regularization using the mean-field gain point of view, you actually regularize the Lipschitz constant of the flow map. So people actually commonly believe if you, after the neural network training is done, in terms of input variable, if you can control the Lipschitz constant of that input variable, you can actually get a better generalization. So that's actually a very interesting formula or interesting connection. We actually, later on, I'm going to show you an experiment that this is actually true. If you do this mean-field gain kind of regularization in the regular normalized flow, which are different normalized flows, because of this formula, you will say this can enhance the generalization of the normalized flow. So let me say a few words. How much time? Okay. let me say a few words about some kind of theoretical statement that we can have. I mean, the first two statements relatively simple. It's basically we say, if we consider about the special type of Mayfield game problem, I mean, for the generalized Mayfield game, we are still working on that. We don't have too much theoretical understanding in terms of the numerical discretization. So if we think about the interaction cost-free case, we can connect this interaction cost-free case to the optimal transport. It's actually essentially related to the optimal transport. The formula is different because you still have the KL term. And you can actually show that if you working on the, remember when we do the normalized flow, we discretize the time as our time discretization. The theorem suggests us, if you solve that in the discretized time, then you linearly interpolate your discretized normalized flow. That linear interpolation actually give you the solution of the real continuous normalized flow. Sorry, the continuous Mayfield game. So the reason is actually for this interaction-free case, the solution of the Mayfield game is essentially the optimal transport. So by the optimal transportation theory, we know the trajectory. If you know the mapping, the trajectory is actually a straight line in the space. So therefore, if you approximate the straight line, if you discretize a bunch of points, you directly connect them to the linear interpolation, that will give you the continuous solution. That's the essential idea. But this is sort of a relatively straightforward argument, which means solve our discretized problem, you can actually do the linear interpolation, you can get back to the continuous problem in terms of time. That's what I mean. Now, let me say some other thing about the approximation behavior of the normalized flow. And people know that if you consider this affine coupling flow, then people know the affine coupling flow satisfies some kind of a universal approximation behavior in terms of approximation and mapping. Then we can actually leverage the existing result to show that if we use the normalized flow to approximate the high dimension Mayfield game problem, I mean, this result is about the interaction-free case. In other words, if the mapping is given, then we can show that if you not use the normalized flow, the result solved by the neural network actually can approximate the result we're looking for, which means the sequence we created is gonna converge to the density you are looking for. So this theoretical argument actually gave us some kind of a partial confidence. Say, as I mentioned, we want to design something with solid theoretical guarantee. This gave us some kind of partial confidence, say this might be a good way to go. And right now, the current estimation is not ideal yet because we don't have network complexity analysis yet. We're working on that. Hopefully, in the near future, we can have a better understanding how complex our network structure can be to approximate the density. But right now, it's sort of like existence proof. So now it's ready to show some numerical results for fun. How much time do I have, Alex? 5 minutes? Yeah. Okay. Let me show some pictures and videos. So one is high dimension optimal transport. So as the picture I show you. So in the table, we actually compute this in the 2-dimension, 10-dimension, 50-dimension, and 100-dimension optimal transport. This dimension is the space, the ground space. So we actually construct this example is actually from this paper, as I mentioned to you, which they choose this very special type of density, such as the cross different dimension, the kinetic energy cost as a result is actually consistent, and M is the matching term. And now you can see that we compare this with in the 2D we have the Euclidean solver. This is the energy of the Euclidean solver, and in high D, of course, we don't have a Euclidean solver. In high D, we only compare with this Mayfield game network. So as you can see that we actually achieve similar accuracy in terms of the kinetic energy term, which means the sort of Wasserstein distance, and the matching term, that because we have this kinetic the KL energy. So our matching term, that energy is much smaller, which means that our matching quality is higher. And in terms of the time consumption per iterations, so it looks like our methods is more efficient, or the scaling is more linear in terms of dimension than their methods. So that's our observation, and the left panel shows the pictures. As I mentioned, the choice of the density is very special, and I just projected 2D. You can see it sort of compatible with your intuition, and if it's optimal transport starting from a Gaussian, you have the Gaussian mixture. You have some kind of a line is shooting on the Gaussian mixture. So the result actually is compatible with the intuition. And now this is another example about the cloud motion. Now we plug in some kind of interactions. It's not the optimal transport. You have interaction means in the middle, you basically have some obstacles. You would like to ask your density to avoid the obstacle. So we also show this, compare this in the 2-dimension, 10 dimension, 50 dimension, and 100 dimension. And this picture is just a 10-dimension case. I show the projection of 2D of the 10-dimension case and choose different strength of the lambda. So the bigger lambda means the density should avoid the obstacle stronger, and the smaller the density may not avoid the obstacle that much. So similar behavior actually we also observed, and our matching term cost is more improved, and per iteration is more efficient. I think this is due to, especially the matching accuracy, is due to in our normalized flow structure, we don't have to compare with the previous method. Over there, they have to use the penalty method to handle the Hamilton-Jacobi-Bellman equation and the continuity equation. And we actually injected this in the part of the network structure, so which intuitively this will give us a more accurate results. So here's something fun. So as I mentioned, this is a multi-group path planning problem. You have like 8 groups, like this picture I showed 2D, 8 groups. So you want this group avoid the collision, but also they swap the location. Okay, so we actually do this in the 2D, 3D. So as I mentioned, so if you think about a PDE problem, each group is 2D. You have 8 group is like 16 dimension PDEs, because each group they actually have the interaction. So we use the Gaussian kernel as the interaction energy. So you can say, if we solve this using normalized flow deep neural networks, the result as I show you in the bottom row, the groups actually successfully switch to location at the same time, meanwhile avoid the collision. And the other one, the last one, this one, is very interesting. So we have 2 groups, right? So if there's no interaction, there's no obstacle, this group, the purple group and the green group, they basically want to move from bottom to the top. If you think about the optimal transport, right, what they do is just to go straight from bottom to top. Now, if we inject this obstacle, like here, we inject the obstacle, and the obstacle is actually far away from the purple group. If there's no interaction between the purple group and the green group, and the green group is going to avoid the obstacle, and the purple group is actually moving directly from bottom to top. But now what we're doing is you have the obstacle, and meanwhile, you ask this 2 group, they cannot have a collision. So it's something interesting happening, also compatible with our intuition. The green dot should avoid the obstacle at the same time, because the purple group are trying to avoid the obstacle to the, trying to avoid the collision to the green dot. So both trajectories get affected. So this is a very interesting example to show us this way actually works in the high dimension setup. And we're trying to figure out some nice application in terms of optimal control in the high dimension and say how far we can go. So here's something we're trying very recently. I mean, we got this result very, very recent. This is a robot arm. I mean, this result may or may not be the best, but I just show you we got this very, very recently. We're working on something related. This robot arm control, so you have a cup, and starting from some location, and you want to design an optimal path to ask the arm touch the cup at the same time avoid the collision. And because of the freedom of the joint, so the problem is actually an optimal control problem in the 10-dimension space. The configuration space is 10 dimension. I will actually apply our normalized flow deep neural network-based approach, you can see that actually this trajectory gave us a sort of reasonable design of the trajectory. And hopefully we can apply this to some real case. We're working on something in the near future. I hope I can share you. So I think my time is almost out, right, Alex? So let me say something very quick, maybe 1 minute. So the other thing, as I mentioned, so at the very beginning of the second part, so because of our the sort of interaction term and the kinetic energy term about the variational Mayfield game problem, as I mentioned, this can give us a hope to enhance the robustness, the generalization of the normalized flow. Actually, we tried some numerical experiments, as you can see here, starting from the Gaussian to the S shape. So the first row is without any interaction. It's just a conventional normalized flow. You say in the intermediate flow, basically, it's not that meaningful. So if you plug in this more control, kinetic energy control, so you will say intermediate flow, you will see the density is going to gradually move from one to other one. And meanwhile, we also check the generalization gap. So this picture actually show you the sort of the Lipschitz constant, Lipschitz bound of normalized flow without the Mayfield game control and normalized flow with the Mayfield game control. So you will see the Lipschitz constant actually can be much more improved, which means people commonly believe if Lipschitz constant of the mapping is small and you have a better generalization. And there's some more picture, and also they share similar behavior. If you do the Mayfield game control, the intermediate flow will show you more geometrically meaningful morphing. And we actually tested this to the tabular data. And we show that actually in the tabular data, we also observe the similar behavior. If you plug in the sort of Mayfield control thing in your normalized flow, we actually try different normalized flow. We consistently observe this Lipschitz constant, Lipschitz bound actually can be improved, and also the result also can be improved. So that's sort of my last page. No, let me use 5 seconds. So we can actually also generalize the whole thing, the computation strategy, because of our projection method, to the manifold setup, which means the domain may or may not be Euclidean, because in the data science, if you want to working on the optimal transport or Mayfield game on the general data, the domain may or may not be Euclidean. And let me skip something. I directly show a picture. And this is a 2-dimensional Riemannian manifold setup. We can compute the optimal transport and also Mayfield game control, Mayfield game problem on the different kinds of manifolds. Our algorithm actually very robust to the topology and something animal for fun. Homer and genus 1 surface, and we can handle the interaction-free case, and also we can handle the non-local interaction case. So that's pretty much I have. I'm going to skip this part. I will skip this. Oh, sorry. Let me quickly summarize. So what we're doing is we propose in terms of conventional method in lower dimension case, we'll propose a projective gradient descent method to solve the Mayfield game problem. We conduct the convergence analysis to show the discretized algorithm, discretized solution when the match size goes to 0, it converges to the continuous solution. And in high dimension setup, we consider trajectory-based formula. We use the normalized flow to parameterize the Mayfield game problem. And this connection lead to a new way of solving high dimension Mayfield game problem. Meanwhile, it also lead to another way of regularizing the normalized flow. And this in our experiments, we show this can enhance the performance of the normalized flow. And last way, I quickly show we actually design a numerical method to compute the Mayfield game problem on the more general setup, which is lower dimension Riemannian manifold. So that's about it. Thanks so much.
Awesome. Thank you so much. So questions?